Okay, so then we'll leave the homework and we'll go into high-speed craft and naval vessels. Of course, I will not cover everything with naval vessels, and it's a very special field, which of course is important in itself. I'll more talk about some, let's say, some concepts that are important more in general, and in particular for ship design, and then in particular some concepts that are important if we are going to look at high-speed craft. And when we talk about high-speed craft, it's normally defined as something going around 30 knots plus, right? That's the normal definition. You can say that a container ship is going high speed when it goes 25 knots because it's much faster than, let's say, a bulk carrier or a tanker, but it's not a high-speed craft. A high-speed craft, you have to get up to about 30 knots in order to call it a high-speed craft, because then you get into some completely different phenomena that makes it possible for this vessel to go very fast. I collected a lot of, let's say, first page of covers of books that have relevance to when you are going to consider ship performance. And of course, when you get into high-speed craft, hydrodynamics is very, very important. Okay? But here, you should be able to see the title of the book, and then you just Google that title, and you can get how to find the book either in the library or buy it at Amazon.com or some other place, or order the book. But I'm not going into all of this. But certainly some of these authors I know pretty well. And now just some very, very simple concepts. And this goes, I'm sure many of you know this very well from before, and some of you who don't have really a strong background in naval architecture, this may be new to you. But when we are characterizing, let's say, a hull of a ship, there are certain parameters. We talk about coefficients, ratios. So this is basic ship design, so to speak. But anyway, I listed this for you, so just to make sure that you know about it. And there's this first one is probably the most important one, and you should have heard about it. It's the block coefficient. So we talk about the ship having a large block coefficient or a small block coefficient. And the way it is, it's defined by the submerged volume of the ship, that is the volume below the water plane, that's V. And then it's the submerged length of the ship, which is called LPP for some reason. And it's the breadth, and how wide it is, and T is the draft, how far down in water it's sticking, right? So it's really comparing the volume of the ship to, let's say, a shoebox, where the shoebox follows the water plane, and it is exactly as long as the ship, the submerged length, and the width, and the submerged draft. Okay? So a tanker would typically have a very high block coefficient, whereas a container ship, which is designed to go fast, has a much more shaped form, and the block coefficient is considerably lower. Then you can do the same thing looking at sections. You can look at the midsection of the ship. In the middle of the ship, you have a midship coefficient, which is the submerged area divided by the surrounding, let's say, square or rectangle, I mean, defined by the width or the breadth of the ship, and then again T, the submerged length or the draft. Okay. So that characterizes, and of course this can be rounded, like this could be a what should we say, a sail ship, which is designed to go fast, or it could be like a box. That would be a bulk carrier or a tanker. So again, a large value is for low speed ships. And the same thing you can do with a waterplane. Look at that area multiplied the waterplane area AM. No, I'm sorry. The volume divided by this is the prismatic coefficient. So that's the volume divided by this section. This area that would just look like multiplied by the total length. So that's the prism shape defined by the midsection, and I don't think this one has really too much interest. But this waterplane coefficient I think is more relevant, and that's the length of the wetted surface, waterplane area, and the width. And you can also see that there's a relationship between these coefficients by multiplying out. So the slenderness of the hull is mainly defined by this: the waterplane coefficient and the block coefficient. So the waterplane coefficient says something about how slender it is in this plane, and the block coefficient, the overall volume, and the midsection coefficient says something about the roundedness of the hull. So that is kind of the parameters that characterize the shape of the hull. But when we now get into hydrodynamics, and I'm not going to talk too much about that, you have other courses that would define this, but there are two numbers that you hear occurring quite frequently. It's the Froude number, and the Froude number is defined as velocity divided by the square root of a characteristic length of the body and the acceleration of gravity g. And this has significance for what we call potential flow. And this is the quantity that is, let's say, dominating the behavior of ships that go not too fast, where the resistance of the ship motion is dominated by potential flow. Then at higher speeds we have viscous internal friction effects in the water, And then we have the Reynolds number, which also depends on the characteristic length and velocity. But you see here the characteristic length is in the nominator, not in the denominator, and it's no square root. And then you have the viscosity coefficient. So we have two types of behaviors. The one has to do when you have a ship, you have to move the water away, right? So when the ship comes here, of course the water has to be pressed to the sides, and that is, let's say, the potential flow motion. But then if the ship moves very fast, it makes turbulence, and particularly makes turbulence behind the ship, where you have to fill in the water very quickly when the ship is passing by. And that's where the Reynolds number, to a large extent, is dominating the behavior. So one is talking about resistance coefficients, and the total consists of one part, which is the residual, or sometimes called the wave coefficient, CR or CW. And then you have the friction coefficient, and R is the force, and 1/2 rho is the density of water, velocity square, times the wetted surface. So in other ways, what you typically would do is to calculate the resistance as the total resistance coefficient, C total, which is the residual and the friction, multiplied by 1/2 rho V square times S. So you see the resistance, in theory, for a given condition in that area, it's a function of V square. But these coefficients are not constant coefficients. You know, they are not constants, but they are relating to a particular condition, or let's say a particular speed range. But the reason why we are working with these things is when we translate from model testing in a basin to a full-scale ship. And, you know, we just have to go out in the corridor to see some of these models. And when you do the analysis or the measurements on the model, and you want to translate that into the resistance you measure in the towing tank, then you have to use these equations in order to translate the resistance you measure to the resistance that the ship will experience in the open sea, the full prototype. Well, that sounds good, but unfortunately the hydrodynamic testing is not that simple, because we have two different scaling numbers. One is the Froude number and the other one is the Reynolds number, and they don't scale in the same way. So you have to add some experience and some correction factors. But typically, if you have a lot of drag, you would scale according to the Reynolds number, and if you have, let's say, a slow-going more slow-going ship, you scale according to the Froude number. So, but how can we see that we have to introduce a lot of energy when we move a ship? Well, we can see it simply by we generate surface waves. And of course, to a surface wave, what is that? Well, it's two forms of energy. It's potential energy, right? Because the mass is moving up and down in the gravity field, and it's kinetic energy, which is the velocity of the water particles, right? So that's, when we have the resistance force and we have a certain velocity, the force times velocity gives us the power that we need for the ship. And that power goes into two things. It goes into making the waves. That's where this potential energy from, potential flow energy is going. And the other part is lost energy, which is the viscous part. So, and this... So for the ship, of course, the ship is experiencing two things. The ship is experiencing not the waves. The waves happen, away from the ship. The ship is experiencing a pressure distribution along the body. That's why it has to use power to force its way forward. And then we also have the viscous resistance, and the viscous resistance has two parts. One part is that this turbulence, which is caused by internal friction in the fluid, that disturbs the pressure patterns along the ship. So that's one part. And the other part is actually the skin friction, which is also depending on the viscosity of the water. Okay? So, for low speeds, it's the surface wave part of it that is dominating, and for high speeds, it's the friction in the water and the skin friction that is dominating. But if you have a fully submerged vessel, depending on how far you go below the surface, but for a submarine, typically the skin friction is the most important. You have very little energy that you transfer to surface waves. Of course, you make some acoustic waves, which are pressure waves also, but that's another item. So submarines that go very deep, that's where you have particularly skin friction and also some viscous drag friction. So that's the resistance force. And this is you can study this, but the total resistance, and these are also expressed by this coefficient C, right? Whether you talk about the force or you talk about the coefficient, those are more or less the same quantities. It's only scaled by this 1/2 rho velocity square and wetted surface. So the residual resistance has the pressure from the potential flow, and then you have a form effect on the skin friction. That is the disturbance from the flow around the body also influence the friction. And the pressure resistance comes from a wave part and a viscous part. The viscous turbulence also influences the pressure. And the wave resistance you can divide into a wave making and a wave breaking resistance. There are different ways of dividing this up. But the important thing is to know that you have the the potential flow part, and you have the friction part, and the friction part consists of a viscous friction where you have turbulence and a surface friction. And this is really when it comes to surface waves, this is a very classical topic that, for instance, was studied by Lord Kelvin, the originator of degrees Kelvin. And these people, these physicists and mathematicians were very smart people. And they worked with many types of problems. And Lord Kelvin was interested in if you dragged a point, or let's say a rod, through the surface, what kind of waves would be generated. Well, he discovered there are two types of waves. One is a divergence wave, which is kind of the plowing effect, where you have waves going at an inclined angle out to the sides. And then, as a part of the drag effect behind the body, you get these transverse waves. Here you see line, dot, dot, line, dot, dot. So that is the crest and the trough of the wave. So he could even calculate the angle of this front of the waves. So you have these two patterns, and when you look at the ship next time, you should know that there are two types of waves, surface waves, generated by the ship. One has mainly to do with a bow, that is this part, the divergence wave, and one type of wave is mainly associated with the aft part of the ship, where kind of the fluid fills in behind, and that's these transverse waves. And to know this is quite useful. So if you look at this picture, you see the divergence waves here, but you also see some waves going transversely here. But I think this picture is even better. This is a duck, right? And the duck has been swimming here. And you see the two different wave patterns. And actually the interaction between these two wave patterns is very important for the resistance of the ship. If you can design the ship for a particular, let's say, the main speed it's going to operate with, if you can design it such a way that these waves cancel each other, that means less energy, right? So if you can design it in such a way, then it will be a much more efficient ship. And if you do testing in the towing tank, you may find, very strange kind of diagram here, expressing the total coefficient of resistance. And of course, what you measure, you can translate now by the scaling effect, that equation that you saw, to a large ship. Okay, but you see here there's some for a particular speed. There's a cancellation effect. So that is obviously a optimal point. For a catamaran, it's interesting. For a catamaran, in addition to this kind of effect, you also have a cancellation effect between the two hulls to some extent. Okay. Some of these things you may have to sit down and think a little bit more about. But it's quite obvious if you think of turbulence, and here is flow around a cylinder, but that's one type of body. Typically you get these eddies, these whirling eddies, and this is what you also see. For instance, this is a computational fluid dynamics numerical simulation. You see these flows going back and forth, and there's also not only the drag effect on the body, but there's a lift effect also, which is quite important, and it's particularly important if you talk about, let's say, floating structure, where you can, if you are unfortunate, you can have a resonance effect between the variable lift, which goes in that direction, and the eigenfrequency of the structure, and that means you are in trouble. And here is for a different Reynolds number. You see these flow patterns. These are experiments. This is a simulation. This is reality. And when you look at this behind a ship, the trace behind the ship, you realize this is rather complicated, isn't it? It's, even with modern CFD, I think we would have lots of difficulties analyzing this flow pattern behind the ship. But CFD can still be used to optimizing parts of the ship, and for instance the inflow to propellers. So I think maybe we'll take a break there. Yeah, I'll take this one too. And with modern computational fluid dynamics, we can simulate, we can solve some rather big problems with millions degrees of freedom, but still that may not be sufficient. And this is a simulation of the divergence waves, and then you see here behind it, well, it almost looks like divergence waves as well, but there's also transverse waves. And this is a program called Fluent, which is used very much. RANS method, Reynolds number average Navier-Stokes. Navier-Stokes equation, of course, is the full equation that is applying to viscous flow. Okay? Both the potential part of it and the viscous part of it. And there's a difference between compressible flow and incompressible flow, and typically if we are talking about water and fluids, then we have to do incompressible flow, whereas in air, like flow around the airplane, then it's compressible flow. Here's a simulation that is done to calculate the pressures on the propeller with modern CFD. There's a method called VOF, which is used very much. Volume of fluid. Okay, so there are different formulations. There's also what's called particle methods, where you actually substitute water by a large number of particles, and you, rather than now I'm getting into something I'm not sure you have heard about, but there's something called the Eulerian description and something called Lagrangian description. In Eulerian description, which you often use in fluid dynamics, you look, let's say you look at the grid and you look at flow in relation to a grid. So you characterize the flow by velocities passing these points in space. Whereas in Lagrangian formulation, you follow the material particles. So with a particle method, you would typically use a Lagrangian formulation. So with that, you can formulate contact problems, breaking waves, and all sorts of things. which sounds very good, but of course you need a lot of particles to describe a fluid, and also unfortunately with the particle method the pressures you get are not too good. Okay, so I'm getting a little bit beyond what you are doing in your courses now, but some of you may later on do research in fluid dynamics, and then you typically would get into these things. So the wave resistance can be reduced by reducing the water plane area of the ship, because that's where you really make the surface waves. Not only there, but certainly that's a critical area. The wave resistance can also be reduced by lifting up the hull. Of course, the less space you occupy in the water and where you have to push away the water, if you can lift it up, then of course you'll reduce the total resistance. Not only the wave resistance. The turbulence part of the viscous effects are particularly important for the aft part of the ship, where most of the turbulence occurs. In the wake, it's called the wake, where the water fills in behind the ship. The bulb of a ship also has some effect on the viscous flow. Skin friction depends largely on the size of the wetted surface area. Right? The bigger surface, the more friction. The water inflow pattern to the propellers is important for their efficiency. And we saw on the picture this turbulent behavior behind the ship. And this is not only at the water surface, but it's also below the surface. And whether you have a laminar flow or you have a turbulent flow into the propellers, that has an effect on their efficiency. Ideally, you would like to have a laminar flow, straight flow lines into the propellers where you generate the power to move the ship forward. The overall resistance of the ship can be reduced by optimizing the hull shape for a selected ship operational speed, and in some cases such improvements can reduce the resistance with many percent. Well, 20% is extreme, but that means that at the begin with you had a hull form that was not very efficient. But certainly with modern CFD, and of course by testing in a towing tank, one can optimize the ship hull. And this is where the advantage by CFD comes in, because with CFD, with numerical methods, you can do many parameter variations. In a towing tank, it's so expensive to do the tests and takes so long time that normally you only test one hull, maybe in the worst case two hulls, or maybe you test one hull and then you modify the bulb at the front and you test it again. So it's much easier to do parametric variations when you have a numerical technique than as opposed to when you test in a model basin. Yeah? So now we come into some fun parts here. How can we reduce the resistance? Well, we have sustension, means how is the ship lifted. And it can be lifted from buoyancy, right? It's simply the weight of the displaced water, right? That's the displacement principle, right? Most ships are displacement ships. They are carried by simply the hydrostatic water pressure. So, for slow-going ships, where you have no particular surface effects that will give you a lift, then you are in this corner. And it can be a normal hull form or a hull form like this, where the buoyancy comes from bodies that are totally submerged underwater, right? Almost like two torpedoes. We'll get into this because this is a particular type of ship which has been used quite a bit in special applications. But then you can get a surface effect by having a hull form that gives you a lift. That is, when you hit the water with a given velocity, the water pressure builds up, and that component of the dynamic component, and now we are not talking about the static component, we're talking about the dynamic component, let's say more the inertia in the water, gives you a lift effect, right? You can think of the water particles hitting the surface of the wetted surface of the ship and pressuring it up because of the inertia in the water. And that's the effect which is very important for high speed. And you can have more or less dynamic lift of a ship. For a very, very large ship, you seldom have this kind of effect. But for smaller vessels, this lift effect can be very, very large. And then you can make this lift effect so large that you lift the whole hull above the water. And that's what you do in hydrofoils, right? You have foils underwater that gives you the lift, and the lift effect is sufficient to lift the whole ship up. So, of course, when it is not moving, then it sinks down and floats like a regular vessel. And you start the whole thing with, of course, you have to have a propeller underwater, but you start by giving it a high increasing speed, and then suddenly you come to a stage where the whole thing lifts up. It's almost the surface effects is certainly like water skis, right? And this hydrodynamic lift is underwater, which is almost like an airplane wing underwater that gives you a lift. But then there's another principle, and that is if you increase the air pressure under the ship, that of course will give you a lift too. So we are not talking about the water pressure, but we are increasing the air pressure. And for instance, you can increase the air pressure by, let's say, 50 centimeters waterhead, and that is half a ton per square meter. So it can be a significant effect from increasing the air pressure under the ship, and there are two types of it. One that is totally relying on air pressure, like what's called a hovercraft, right? We'll look at that. And there's another type which is a semi-hovercraft called SES, where you have a twin hull and you increase the air pressure between the hulls, and you have some curtains in front and in the aft part of the ship. Okay? We'll look at that too. So, so in one way, the ship can be more or less hanging in the air depending on which principle you are applying here. So And we are going to talk about different hull forms. When you have only one hull, you call it a mono hull. Mono for one. Mono hull. And a catamaran has two hulls, right? Which are somehow combined above water. And you have, from catamaran, you can go to a trimaran, and the word tri means three. So you have three hulls, right? And normally these are not exactly the same size. Then you have what's called the asymmetric trimaran. Well, asymmetric is not really the best word here, but it refers to that these outer parts of the hull are often much smaller than the part in the middle. So, if you have a very slender ship, you can reduce the resistance also for a displacement hull, right? But if you make it slender, it becomes rather unstable in roll, right? Because it's the waterplane area that stabilizes these rotations. That's what we saw as a function of B in our homework, right? So, and then you can have various combinations, and you can reduce both the wave resistance and the drag resistance by having a bulb of some sort. And you can even have a bulb at the stern, the aft part of the ship. And you can have foils, hydrofoils, right? That gives you a lift force. Or you can increase the air pressure under the ship. That's the air cushion principle. So we look further into this. And of course, some of these technologies now are getting to be more and more like aircraft technology, these lift principles, and the importance of a light structure. Because if you are going to have these lift effects, the structure has to be light. So design will look very much different. I think I'll skip this, but here you can possibly read this from a displacement to a surface lift effect, and then you have air cushion, and it's hard to read. I could read it on my screen. Well, anyway, you'll find some, hopefully it will be clear enough in the copy you have. And you'll find some terminology there that applies to these different classes or ships, and we will describe some of them. So typically, if you have a planing body, it will be rather flat under. I used to have a motorboat like this myself for 20 years. I sold it 2 years ago. It's very strange, when you go slow, you can feel by giving more power to the boat that resistance is increasing. The engine is working hard, to overwin the resistance. But then, when you come to a certain speed, the whole hull lifts up. Suddenly, you don't give it more throttle, you give the same amount of gas to the engine, but suddenly it lifts up, and the resistance is much less, and the speed goes up very, very fast. So that is from being let's say, where you're carried by the hydrostatic forces. You are, after a while, when you come in a water at the planing position, the main lift comes from this dynamic effect of the water hitting the surface of the ship or the vessel, right? And of course, if you look at a racing boat, it's touching the water, and they even have a certain wing effect, where the ship also has an aerodynamic lift in addition to the surface planing effect of the water. And sometimes you have seen accidents maybe on television where these boats hit a wave and they go up, and so the angle of attack of the boat is increased, and it gets such a high lift that it goes up in the air. And so in the worst case, it goes like this, which of course can be fatal at these very high speeds. And getting into some military applications. I have some pictures here of, let's say more futuristic warships, but they are actually built, some of them. And what is showing here is what's called a wave-piercing design. And what is a wave-piercing design? Normally, on a ship, you have a bow that looks like this, right? And if you have a wave coming in here, it gives you a lift at the front, and the advantage by that is that you lift up the deck and you don't get so much water on deck, right? And one dangerous situation for, let's say, a bulk carrier is when you get a big wave coming up on the deck and possibly crushing what is it called? Hatch covers, thank you. The hatch covers, they have to be designed for a very high water pressure, right? But there have been many accidents with bulk carriers where the hatch covers have collapsed. Okay? So, and typical for an elegant cruise ship also, you have these big flares at the bow, which looks very nice design-wise. But it has one disadvantage, and that is that you'll get high pitching accelerations when you hit these big waves, right? Because you get such a big lift. So an opposite principle is to have a bow that goes like this. And of course, if you have a big wave coming in here, it cuts right into the wave. So it cuts through the wave, and you won't see that on a bulk carrier, but certain for a warship, where you don't have that kind of worry when it comes to the deck space, it's very solidly designed, then you can allow for these big waves coming up on the deck. So it's not necessarily more efficient from a resistance point of view, but it changes the behavior in seakeeping. And what is seakeeping? Well, we talk about ships, we talk about resistance, like you've talked about quite a bit during the previous hour. But seakeeping is how the ship behaves in real sea, right? Where you have waves. We are not talking about the waves made by the ship. We are talking about the waves in the ocean, and how is the ship behaving in the storm or in a particular sea state. And typically you have to analyze a ship for waves coming in different angles and how it, is heaving and pitching and rolling in these conditions. That's what we mean by seakeeping, how it behaves in real sea states. And of course, this kind of ship behaves completely different from a ship with a flare. It's more stable. So if you are looking for a stable platform, and sometimes in the Navy they refer to the ship as the platform, it's the platform for the weaponry on the ship, right? That's why they call it the platform. So it can be more stable by having this kind of design. And of course, as you see, for instance, here, it's very shaped. The water plane coefficient would be rather low in this case, right? You see, it's a very slender shaped body, as opposed to a tanker, which is almost like a box, right? So the wave resistance also is less with this kind of hull shape, and therefore you can go higher speed. And of course, the bigger the ship is, the more suitable it is for higher speeds. So this kind of principle we applied to the case of the cruise ship, the twin hull or catamaran type cruise ship that I showed you once before. Right? So hopefully this kind of hull form will make it more stable and not heaving and pitching so much when it comes to being out in rough weather. Okay. And then, since we are, this course is about innovation. I'll show you some things people have been thinking about when it comes to skin friction. And skin friction, let's say that this is the ship, here is the ship. Here's the ship, right? And it's moving with a velocity, let's say v, right? And here's the water, and it's not moving at all. That is, of course, it's pushed away, but it's the ship that has the velocity and is plowing through the water. And if you look at the relative velocity, okay, if at the surface here, you can think of the water molecules being attached to the surface of the ship, and when you come out here, then the velocity is very low. So you can think of a velocity profile that looks like this. So here, the water molecules at the surface have the same speed. Let's say there's very little slip, same speed as the ship, right? So this is the velocity, and this is the distance from the ship surface. And if you translate that into, you see, it's the velocity gradient next to the surface of the ship that is important. Because it's a viscous fluid, it has an initial internal resistance, and you can translate this into a shear force, where the shear force is building up to a high value here, and then it's because it's depending on the velocity gradient. So you can think of the water, even though it's a fluid, it has this kind of shear force behavior, and this shear force is experienced as friction by the ship. It's the velocity gradient and it's the viscosity of the water that gives this shear force, which is unfortunately highest next to the outer surface of the ship, the wetted surface of the ship. So that is that friction part that we have been talking about. So what can you do to reduce the friction? Well, how do you normally reduce dry friction? You use some oil, don't you? Right? So there, one idea is then to apply not oil but a polymer. And polymer is long molecular chains, right? So by applying polymers, they want to break down this shear layer, right? And so they have made lots of small holes in the surface of the ship, the wetted surface, and they inject some polymer powder and mix it with the fluid, probably just water, and then you have a given part per million here, and this is injected out through a hole to the surface, and that presumably reduces the friction somewhat. And this is patented like crazy, right? But do you think this is a practical thing? I think after a while you'll have trouble keeping these holes open. And of course, I think people would object to having these polymers being sprayed into the water, right? But it can be shown by experiments that you can get some reduction. Here's another one, another patent. And here they not only have these holes, but they even make the surface kind of a jagged form, right? And this should then increase the efficiency. And but you see, this is getting to be very, very complicated. And of course, you can ask, well, we would like to protect our ship against corrosion, so we have to paint it, right? How do you think this work with all these small holes for injecting? To me, it's a mystery. But of course, if you make the hull of, let's say, aluminum, you don't have to paint it. But people go to lengths, they have some ideas, and then they don't think too much about the practical aspects. Here is one concept which is also has been used to, which is simpler, to reduce the skin friction. And what do they do? Well, they have small holes, and then they pressure air, so they get small air bubbles. And here you can see the boundary layer. You see the air bubbles under the ship. And these air bubbles will reduce the viscosity of the water, right? Because the shear force we're talking about depends on the viscosity. The higher viscosity, the more shear force. So they can reduce the viscosity of the water by injecting air, and they've done, experiments to show that you can reduce the skin friction this way. And as a matter of fact, this has been tested on a large scale. For a real ship, it's probably a Japanese. What do you think? Seiyun Maru. Does that sound Japanese? Yes. We say so. And here, under the bottom of the ship, they are injecting more air bubbles, right? You see a flow of air bubbles. And again, they can demonstrate some reduction of the friction. But again, you can also come up with some questions regarding a technology like this. One question is, well, let's say the ship has a draft of 10 meters, and to pressure air bubble, down to 10 meters, you have 1 bar pressure that you have to overwin. So, of course, you have to use some energy to pump the air down there. I know they have been looking at, for instance, pressure from the engine and pumping some of the exhaust down there, but that may not be a good idea when it comes to the pollution aspect. You should rather clean the exhaust than using it directly under the ship. So, but I know this is also considered for large ships. So it may be a little bit more realistic than using polymers. Okay. And then some other principles. I talked about submarines not making much waves. Of course, it depends on how far below the surface. A fully submerged submarine that's just below the surface will make surface waves as well. That's for sure. But it will be less than in a case where you are cutting the water surface. And what one is doing in this concept is to combine, let's say, a torpedo-like body with a regular hull, and when you combine the two, it looks like this, right? So you have a larger part of the hull being submerged underwater, making presumably less waves, and then also more suited for a high speed. But obviously also you increase the wetted surface area by having such a shape. So the friction will go up. So this has been tested. I don't think it's been a great success. And it's quite impressive to see also hydrofoils, what they can do. Lift up pretty big ships. And if you go, let's say, 30 years back, hydrofoils were the new thing, because they could go fast. But what one has learned now is that hydrofoils they can be good up to certain speeds. But I think it's around 34, 35 knots. They typically becomes less efficient because you get so much drag on these foils. Okay, so it's not really for the very, very high speed vessels, but it's for intermediate speed. Okay. I don't think we see so many hydrofoils these days, but we see a lot of catamarans and other high-speed ships that have a surface effect. One could think that this is you know, if somebody's shooting a torpedo here, it would go right through, but it's normally the magnetism that triggers the explosion, isn't it? I think so. So catamarans are really the thing, and with the catamarans you have two very sleek, very narrow bodies, two narrow hulls that have less resistance, right? Because the resistance is very much a function of the width of the hull. And you get a very stable geometry. This is from the city of Bergen, west coast of Norway, and there's a lot of these catamarans that are serving islands and going into the deep fjords of Norway. And they are efficient, normally built in aluminum, to make them light, but sometimes in FRP, fiber reinforced plastic, or even carbon fiber reinforced plastic. If you really wanted to make it light, then you go to carbon fiber rather than glass fiber. But this is an example of a ferry that's built on carbon fiber. And I think I dare say that in Norway when it comes to marine technology, there's always been a lot of experimentation. And particularly in the western part of Norway, people are very industrious and they are very creative sometimes. And so they develop new concepts for ships. So this is Brødrene Aa. I think they are now a part of the Ulstein group. Then you have these specially shaped where you try to reduce the water plane area. That's often called a swath if you have very large volume underwater. Well, in this case that applies to the forepart of the ship, but from the middle and beyond it's like a catamaran type hull, twin hull. And you see this one is one that has been operating in Sweden and in Ireland. And we'll look more into this. This is an Australian design, and Australians have been also leading in high-speed craft. This is what's called the INCAT, CAT for catamaran. And there are all sorts of applications for fast ferries in Australia and other places too. And here you see a military version of it. So let's look at this HSS high-speed ship, which is a ferry built in aluminum. You can see it's quite large, 127 meters length, 40 meters wide, 360 cars, 1,500 passengers. There were two built of these. I know it quite well from it. They had DNV class, and there was a lot of new technology that was developed for these catamarans. Later on, they've had some problems because of fuel cost. You really burn a lot of fuel when you have such a large vessel.
Is there any better reason to use aluminum?
The advantage is weight, right? Weight is very important. So typically, this and the other one you saw, INCAT, built in aluminum. I think there are regulations that make it difficult to build very large ship in fiber reinforced plastics because of the fire problem. So, of course, that doesn't matter so much for a military vessel, but if there's some when it comes to fire and distance from where you have people down to the water, there are some regulations that makes it difficult. So aluminum is what is mainly used, and typically on the INCATs, and I think here too, is gas turbines, engines. So you have a lot of power in relation to the weight of the engines. The performance weight ratio is very important. But since you go so fast, you hit a lot of waves, fatigue is a big problem. Cracking of aluminum. Looks like a mouse. Yeah. So you see different versions of it. So this is the Australian design, right? Military version. And of course, this shape here is when you are into rough sea and hit a wave, you use this hull shape to cut into the wave so you don't get too much slamming on this wet deck. You can imagine if that was completely flat and you had a big wave hitting under there, the impact is, the shock is very large. So, to soften the shock, you have this cutting underpart. But again, these can also cross the oceans. And I know some of them trade in Australia part of the year, and they trade in other parts of the world other parts of the year, right? But powering is a big problem, to have the machinery work. And then we also have to remember accidents, right? So this is one of the ferries you saw in the picture from the city of Bergen. And this one is called Sleipner. It was an oil platform that was called Sleipner that went down, right? And it hit underwater rock in bad weather, 16 people killed. The problem is that when you go high speed and there's rough water and there's a lot of water spray, the visibility is not very good. In this case, they had been trafficking there so many times, experienced captain, but somehow his mind obviously was slipping, and they ran into a place where they knew there was a rock. And in this case, you see part of the superstructure. I think it's fiber reinforced plastic. Very bad accident. Okay. Let's do swath and then we continue in 1 week. So small water area, twin hull, right? This is kind of the torpedo shape, right? You see these? And the whole idea is to reduce the water plane area and generate less waves. So the advantage is reduced resistance, but you can, since you now know how to calculate the roll frequency and stability, right? you can see that certainly the stability of the ship, since you have a low water plane area, right? The water plane area is what stabilizes the ship, and since it's very small, it's the stability in roll is not so good. And of course, another thing is that it has, since the water plane area is small, and if you put a lot of load on it, it will go down. So the load capacity on a swath is highly reduced. So, somebody may present to you swath as, fabulous because it reduces the resistance. But then you always have to ask, well, there are some advantages, but what are the disadvantages, right? Obviously, there are disadvantages too, right? So I don't think these are very good in rough sea. Of course, you can have winglets, you can have dynamics stabilizers on something like this. But in rough seas, I don't think that does the trick. And this is a monoswath. That's kind of a strange word because TH stands for twin hull. But here you see this submerged body, and you see a combination of a hydro lift. You see these wings here, and this submerged body. This looks very unstable to me. Huh? It's like standing on one leg, isn't it? Of course, it has little winglets here, so that helps in dynamic stabilization. But you can imagine if you are in rough seas and you have problems with those stabilizers. I wouldn't like to be on board of that. No. So, creative, yes. Solution for the future, not necessarily. No. Okay.